This video shows the process of incremental acquisition of demonstrations for generating manipulation plans by exploiting the screw geometry of motion and bandit optimization. Given a region in the robot's workspace, there is no existing work that tells us how many demonstrations would be required to confidently execute any given task over this region. Thus, the objective of our work is to incrementally obtain a sufficient number of demonstrations such that the robot can later use them to successfully generate manipulation plans for any arbitrary task instance in the entire work area with high confidence. In our experiments, we have used pouring and scooping as examples of complex manipulation tasks using a tabletop environment. The region of interest is the red rectangle. Consider the task of pouring from a soup can to a bowl. The kinesthetic demonstration provided by the user can be decomposed into a sequence of constant screw segments as shown on the right. Different colors denote different screw segments. Using these segments and a bandit-based sampling of the region, we generate the belief of the robot about its ability to successfully perform the pouring task, which is shown as a probability heat map over the work area. We define self-evaluation as a process of the robot evaluating the likelihood of manipulation plan generation for any arbitrary task instance using this current set of demonstrations, and in the process identifying the region of the work area where plan generation is most likely to fail. This entire process is repeated to incrementally acquire a sufficient set of demonstrations which can be used by the robot to successfully generate motion plans with high confidence over the specified work area. Next, we are showing how the robot's belief about the success of plan generation evolves with the incremental acquisition of each demonstration for the coding task. We visualize the robot's belief with a probability heat map over its work area. The darker regions are the ones where plan generation is more likely to fail. This is what its belief looks like after acquiring the first demonstration. The green and the red dots represent positions of the red bowl during different coding task instances where plan generation succeeded and failed respectively. We pick one of the failed task instances from the darkest region where the robot's arm is most likely to hit its joint limits and use that location to collect the next demonstration. This is how the robot's belief changes after acquiring the second demonstration. And it changes again after acquiring the third one. At this point, we stop collecting further demonstrations as the robot has achieved a prescribed success rate of 95% in its work area. Using these three demonstrations, the robot can now successfully perform arbitrary pouring tasks in its work area with high confidence. We are showing 4 such pouring task executions. Similarly, for the scooping task experiment, the robot required 4 demonstrations to achieve the 95% confidence. Here, we are showing the acquisition process and the corresponding evolution of the robot's belief sequentially. Finally, we used the collected demonstrations to perform arbitrary scooping task executions. We also performed an extensive user study with 22 non-expert users, providing demonstrations with and without the guidance of our proposed method. The objective of the study is to show the effectiveness of our method in reducing the number of required demonstrations to achieve at least 95% success rate with high confidence. Our algorithm helped reduce the number of demonstrations more than 50% for both the tasks, with only 5 to 6 examples were needed on average with the guidance of our method. Furthermore, as the distribution shows, the variability between the participants were much smaller in the guided trials than the unguided ones. Thus, self-evaluation also ensures more uniformity in the teaching outcome of the participants, despite potential individual differences in their ability to provide demonstrations.